Biology 1108, Presentation 16, Body Defense. Body defense is an issue of humans defending themselves against foreign invaders. And those foreign invaders might be viruses, might be bacteria, might be parasites. But a large part of our body defense mechanism is based in our lymphatic system. So we'll take a very, very quick look at that first. You might remember that the lymphatic system is a circulatory system that is roughly parallel to our own blood circulatory system, though nowhere near as extensive. And the lymphatic system does not carry blood, rather it carries a fluid that is, for all intents and purposes, identical to our blood plasma. If you take a look at the figure at the right, you will see a number of green vessels indicating the presence of the lymphatic system, and it is largely concentrated to the midline of the body. It is nowhere near as extensive as the blood circulatory system, but it plays a number of very important roles. Let's take a look at the components of the lymphatic system. We have lymph vessels. There are lymph nodes, which are aggregations of lymphatic tissue found located in the armpits, in the groin, in the midline of the body, and in the neck. Now, taking a look at lymphoid organs, there are specific structures found in our body that do qualify as part of the lymphatic system. These include the thymus gland, which is located up in the neck, and that is largely responsible for the maturation of T lymphocytes. There's the spleen, and you'll see it to the right, the illustration there on the left-hand side of the body. Its job is to largely retire older red blood cells and remove them from the blood circulatory system. And then there are the tonsils, located in the posterior region of the mouth. I mentioned there were a number of important functions of the lymphatic system, and one of the more important functions is as a fluid reservoir. Obviously, in our bodies, there are plenty of situations where we need to balance fluid composition in our various tissues and our organs, etc., and that fluid will come from the lymphatic system or can actually be stored in the lymphatic system as well. The lymphatic system will function in lipid transport from the small intestine to the cells of the body. You might remember from our presentation on digestion the packaging of triglycerides, fats, as transportable particles called chylomicrons. Those chylomicrons enter into the blood circulatory system because there is an interconnection between the lymphatic system and the blood circulatory system. We'll take a look at that in a second. Now, look at the third bullet point. The lymphatic system is the home base for our immune system. Body defense is largely centered in our lymphatic system. Finally, bullet point number 4, the interconnection with the blood circulatory system. The illustration at right is fairly detailed, and I am not going to require you to know the specifics of right lymphatic duct, or there is a left lymphatic duct as well. What I do need you to know is that the lymphatic system empties ultimately into a major lymph vessel called the thoracic duct. And I need you to know that that thoracic duct, which is, as the name implies, located in the thoracic cavity, does interconnect with the blood circulatory system in the upper port of the thoracic region. This slide represents a bird's eye view of our body defense system. There are actually two major aspects of body defense, and it's going to be very, very important that we understand exactly what those differences are. And in the next few slides, we will be delving into the specifics. First, there is what is referred to as innate immunity or built-in immunity, and that particular form of body defense is immediate. In other words, if something arrives on your doorstep, be it a bacterium, be it a virus, be it a parasite, your innate immunity system will essentially immediately begin dealing with it. It does not require a specific recognition of the foreign agent. All you need to do is distinguish that thing as being foreign, belonging to something other than yourself. Now, this boils down to the presence of certain large molecules on cell surfaces. And those large molecules are commonly referred to as antigens. They are, for the most part, proteins. And you might remember that proteins are really big molecules, and they do have a presence in membranes. Well, the fact of the matter is in any individual, we have a set of proteins in our cell membranes that identify as being ours. And my cell surface macromolecules are different from my neighbors, and mine, while they are going to be somewhat similar to my son's, there's going to be a certain degree of difference. So the fact of the matter is your body has a very, very good idea of what these macromolecules are on your cells. Now, if you take a look at the bullet points under innate immunity, you will see the last one says major histocompatibility complex markers. Sometimes they're referred to as MHC markers. That's the official name for these large macromolecules found on your cells that identify you as being you. That's why I've got the word self in parentheses down there. Now we take a look at the third bullet point. Fact of the matter is that if something shows up on our doorstep, it's going to have its own unique set of cell surface macromolecules. And like I said before, we're going to call those antigens. So antigens label something as being non-self or as being foreign. MHC markers label a cell as belonging to self. And so it's the ability to distinguish between self and non-self that's critical to this thing that we call innate immunity. Innate immunity is considered to be probably the more primitive aspect of our body defense mechanism. The second that's mentioned here is something called acquired immunity, also known as adaptive immunity. And in this case, you are actually going to specifically identify the thing that is attacking you so you can remember what it is and attack it much more effectively if it ever shows up on your doorstep again. So you will see under acquired immunity, it will require an initial exposure. There will be a slow primary response, which involves your immune system being able to recognize and get used to the foreign invader. And then if you ever should get that foreign agent again, you would have an immediate secondary response because your immune system recognizes it and is able to mount an effective attack. And in many cases, destroy the foreign invader before you are even aware of the fact that you've got it. So basically, this particular form of body defense requires a specific recognition of the antigens that mark that invader. So for example, you're going to be able to distinguish between bacterium species A, bacterium species B, and virus C. And in each of those cases, you would have a specific set of weaponry to cope with it. Now we'll take a focused look at innate immunity. And we will be talking about these non-specific body defense mechanisms. They will include passive barriers, the inflammatory response, various cells that will swallow the foreign invaders. We're going to call them phagocytes. And finally, protective proteins. We'll see these on the next few slides. Passive barriers function by not doing anything at all. So you've got no needed antigenic recognition. You don't even have to distinguish self from non-self. These barriers include your skin, mucous membranes, the mucus itself that you might find in your nose or upper respiratory tract, lysozyme, which is an enzyme found in tears, saliva, and blood that has the capacity of breaking apart certain bacterial cells. A variety of flushing mechanisms would include urine, would include bowel movements, would include tears, and then finally pH mechanisms that would be found, for example, in your digestive system, or at least in females, in their lower reproductive tract. So in each of these cases, you're not distinguishing between self and non-self. You're just essentially establishing a physical barrier to prevent something from getting into your body. Most of us are familiar in some way, shape, or form with the inflammatory response. You get a paper cut and it swells, it gets red, and it hurts. That's the inflammatory response. Inflammatory response a lot of times is associated with wounds, but the inflammatory response is also sometimes manifested as an allergic response to something. So let's take a look at what the inflammatory response actually involves. There is a substance known as histamine that's produced by a variety of cells found all over the body called mast cells. A mast cell is a cell that will produce this histamine in response to the presence of foreign agents or foreign antigens. So you take a look at the mast cell illustrated at right, and you will see the production of histamine there. And histamine is a chemical compound that will promote a number of different things. First, vessel dilation. That refers to blood circulatory vessels, and that will increase fluid delivery to the surrounding tissues. Then you'll see the second bullet point there reading vessel permeability, which means that the fluid inside the blood vessel, the plasma, will very easily move from that plasma into surrounding tissues. So there's two operative terms that you can actually write next to these two bullet points. In the case of inflammatory response, next to that first bullet, vessel dilation, you want to write down the word redness, because an increased delivery of blood to an inflamed area is going to increase the amount of redness in that tissue. And then write down the word swelling next to vessel permeability, because when you get that cut, or you get that cat scratch, or you get that injury that all of a sudden not only becomes red but swells a bit, that's because of a change in the permeability of those blood vessels. Now, the benefit to vessel permeability and the benefit to vessel dilation is the fact that you're going to increase the delivery of defensive cells to that area. So my next bullet point here concerns white blood cells called leukocytes. And we had mentioned these in the context of our presentation on the blood circulatory system. And there were a bunch of different leukocytes, many of which we didn't even identify, but the ones we specifically identified were neutrophils and were monocytes. And we will be focusing on these in a little bit. But you will remember that monocytes basically need to become activated, at which point they become big cellular vacuum cleaners that we'll call macrophages. Now, there's one other thing on this slide, and that is a series of substances that are produced also in response to the production of this histamine. And these are substances called pyrogens. Pyrogens are substances that actually encourage a rise in your body temperature. Most of us run around with a body temperature of 98.6 degrees Fahrenheit, but you get yourself a fever, and that will go up to 101, 102, sometimes even high as 103 or 104. Now, once you exceed 103 or 104, then you're kind of a dangerous area. But the fact of the matter is, most of us need to re-examine fever from one very important standpoint. Yes, it's inconvenient, and yes, it is a sign that you are sick, but do you really want to bring that fever down? Maybe not. Now, reason why is because the fever is an adaptive response of your body to basically create an environment that is inhospitable to the bacterium that's trying to infect you. The bacterium gets inside of you, it's on your doorstep, and it's taking up its existence inside of you. 98.6 degrees is optimum for the bacterium. As soon as your temperature goes up to 101 or 102, that bacterium is not so happy. That bacterium might not be able to divide as regularly as it would. So it basically compromises the bacterium a little bit so that your other body defense mechanisms might have a little bit better chance at destroying this foreign invader. Okay, we're going to be looking at phagocytes. We mentioned that not too long ago. We'll look at neutrophils, we'll look at monocytes, and these will both be reviews. Then we'll be looking at natural killer cells, and I'm going to already just mention them now. So you might want to write this next to this bullet point here because there will not be a slide designated for natural killer cells. Natural killer cells are a group of white blood cells, and their job is to run through the body and destroy affected body cells, that is, our own body cells that have been damaged or are in the process of being infected, and they will also take out virally infected cells. So as a consequence, what they're doing is they're kind of vacuuming up the injured and the affected so that the agent, whatever it might be, doesn't spread the surrounding tissues. I mentioned that we were going to focus on these phagocytic cells, and so let's re-examine neutrophils. You might remember this slide from our presentation on circulation. Neutrophils are the most abundant white blood cell in the body. They are part of our innate immunity system, and their job is to perform phagocytosis. In doing so, they will digest the foreign agent that they phagocytize by digesting it with a series of enzymes commonly referred to as peptidases. Once again, a review about something that we've seen before, monocytes. The largest of the leukocytes, these are ordinarily not terribly active, but in the presence of foreign invaders, they will then become activated as macrophages, big, giant, phagocytotic vacuum cleaners. And in the old days, they used to be referred to as dendritic cells, and scientists actually made a distinction between the two, but the distinction at this point is kind of questionable. Their job is to perform mass phagocytosis, and perhaps the most important thing they do is that once they have vacuumed up a bunch of these foreign agents, they will present those antigens to the rest of the immune system so the immune system is able to recognize and specifically identify that foreign agent. So, for example, the antigens on bacterium A would be displayed to the immune system. The antigens to a bacterium B might be exposed to the immune system, and those antigens are exposed to the action of these macrophages. Okay, here's my chance to revisit this notion of natural killer cells. They're sometimes referred to as NK cells. They are a type of lymphocyte, but they're located primarily in the lymphatic system, and they will be released to basically take out tumor and virally infected cells, cells that are potentially dangerous if they are allowed to continue in their destruction. So no prior activation is required. The natural killer cells travel through the body looking for weak and infected cells that need to be removed. Now, on this particular slide, I also mentioned two types of lymphocytes, specifically T lymphocytes or T cells and B lymphocytes, also known as B cells. And we mentioned these briefly once again in the context of the blood circulatory system. But these are going to be extremely important once we shift into a look at acquired immunity, which is sometimes referred to as adaptive immunity. We may have mentioned once upon a time that T lymphocytes or T cells are really, really important in a feature of our acquired immune system called cell-mediated immunity. And B lymphocytes are really, really important in a related aspect of acquired immunity called antibody-mediated immunity. In both cases, these lymphocytes, T cells and B cells, need to be activated. And as we look at them, we will realize that there is some degree of crosstalk between T cells and B cells. For example, under T lymphocytes, you will see a bullet point that says helper T cells activate B lymphocytes. In other words, if a foreign invader gets on your doorstep, and you've seen it before, the T lymphocytes will essentially carry that information to the helper T cells, which will in turn carry the information to the B lymphocytes, so you might be able to crank out antibodies against that particular foreign invasion. All right, back to our look at the innate immune system. We've mentioned passive barriers, we've mentioned the inflammatory response, we've mentioned a variety of white blood cells that defend us against things that qualify as being non-self. We're now going to turn to a group of proteins that actually protect us as well. These are referred to as the complement system. The complement system is a collected group of proteins that do a number of important things. The first thing they do is when a foreign agent gets on your doorstep, they will coat the foreign agent and actually enhance the phagocytosis process. It's almost like putting butter on a pill. You can basically give it to a dog or give it to a cat much more easily. Same sort of idea. But these protective proteins, these complement proteins, will actually also form what are referred to as MACs, which stand for membrane attack complexes. It's nothing more than a series of proteins that will form a hole in the membrane of the foreign agent. If you take a look at the very bottom illustration on the right-hand side of the slide, you'll see what looks like a lifesaver. And that lifesaver is essentially composed of these MAC proteins that are forming this hole, and that hole leads to the bursting, the lysis of that foreign agent. There's another bullet point on the slide, and it mentions a substance called interferon. Interferon was essentially discovered back in the 1980s, and it is a substance that stimulates the production of viruses that will inhibit viral replication. So we do have a specific antiviral mechanism built into us, and it's fairly effective. This substance called interferon basically inhibits the virus's ability to replicate itself, which means it might not be long before you get better on account of the formation of the substance called interferon. It also happens to improve the response of NK cells as well. When we think about our body defense mechanisms, got to keep in mind that these different mechanisms we've been mentioning are not going to happen sequentially. They oftentimes happen all at the same time. There's an awful lot of what I had called crosstalk before between different aspects of our immune system. So, for example, the inflammatory response connects with phagocytosis. Phagocytosis connects with the inflammatory response. Phagocytosis is also going to connect to adaptive immunity. So the bottom line, if some foreign agent shows up in your body, it doesn't take long before all of your immune system specialties are operating against that foreign agent. Now, in this particular slide, we are going to start to scratch the surface on what we're going to refer to as adaptive immunity or acquired immunity. It is the idea that when something shows up in your body, you're able to specifically identify it and then remember it, so that if it ever shows up on your doorstep again, you will be able to effectively destroy it many times even before you're aware of the fact that you are sick. That's why we use the word immune. You say you're immune to chickenpox, you're immune to measles, you're immune to diphtheria, you're immune to all of these different diseases, primarily because you've been vaccinated, or at least in my case, you once had the disease as a child. But the fact of the matter is your body is now able to respond to that agent, should it show up on your doorstep again, and deal with it with a bunch of weapons that are specifically designed for that foreign agent. So before that foreign agent even has a chance to have a foothold in your body, you've destroyed it. So the characteristics of what we're going to call adaptive immunity or acquired immunity or specific body defense is this recognition of specific antigens, and it begins with an innate response. If you take a look at this slide, on the right-hand side of the slide, you'll see an illustration of big, fat macrophage. And that macrophage is phagocytizing the bacterium. Now, once that bacterium gets phagocytized, if you look at the little bitty number 5 on the illustration, you will see some of the cell surface proteins, what we're going to call antigens, being displayed on the surface of the macrophage. So then what happens is once the macrophage has done its job vacuuming up those bacteria, it will parade through the body displaying these antigens, at which point a lot of other different cells, including lymphocytes, are going to be exposed to those. And once that exposure occurs, then you can actually specifically identify that particular bacterium if it should ever show up again. So the key to effective adaptive immunity is to have an initial exposure to this foreign agent. Then at some point later, if it should ever show up again, you can effectively deal with it. So I'm looking at this chart on the right-hand side of the slide, and you see a vertical axis of the chart showing you how many antibodies might be present in the blood. And then I've got time going across the bottom. And you'll notice there's this thing called the primary immune response where you get infected on day 0. And by the time day 14 comes along, you've maxed out on your primary response. I'm going to suggest that at that point, you've probably gotten rid of the foreign agent, and at which point the number of antibodies are going to decrease to the point of where you really don't have to worry about it. Notice the primary immune response is gradual, it takes a certain amount of time, and it only results in a certain amount of antibody units being made. In other words, it gives you a certain amount of protection, certainly enough protection to fight off the agent once you've been infected with it. So like when I was a kid, I got chickenpox. And I had chickenpox probably for about 2 weeks, and I was miserable. But during that entire time, my primary response was dealing with those chickenpox. So when I got done, I did get better. It took a little bit of time. But what I want to do now is I want to look at the secondary immune response. Let's suppose I had chickenpox when I was 4 years old, and I got over it. Now I'm 6. And I bump into some kid at school who has chickenpox. So I've got chickenpox showing up on my doorstep a second time. But you'll notice that in the secondary immune response, the response is almost immediate. The reason is because my body has been exposed to this thing before, and I have almost immediate recognition. And within 3 days, I've got about the same amount of antibodies I made before. In 7 days, I've got 4 times that amount. So I'm actually really quite effectively building up all this stuff against this chickenpox organism. And it's not going to cause me any problems because I'm going to get rid of that organism before it actually creates the set of symptoms that I might refer to as chickenpox. So I might not even know that I'm being exposed to chickenpox at the age of 6. My body effectively deals with it before I'm even aware of that fact. Now we will talk about the major aspects of what we're going to call antibody-mediated immunity and cell-mediated immunity. In antibody-mediated immunity, what we're going to see is the B lymphocytes in our lymphatic system are going to be involved. And they are going to ultimately create a number of different cell types that are going to help us in combating this foreign agent. Now, the name antibody-mediated immunity, also sometimes called humoral immunity, involves the production of antibodies. Our B lymphocytes do not directly attack or kill the foreign agent, but they will contribute to the formation of these proteins called antibodies that will do the job for us. Now, the pattern of how this happens is called clonal selection theory. We're going to explain that. We're going to understand that clonal selection theory is true for antibody-mediated immunity and B lymphocytes, but we're going to see it under cell-mediated immunity and T lymphocytes as well. So our very first step in clonal selection theory is our B lymphocytes are going to be exposed to the antigens of this foreign agent. You'll remember that macrophages do that job. They are the cells that present these antigens. So if I were you, next to exposure, I would write down macrophages. Now, once our B lymphocytes have been exposed to those antigens, only a few of our B lymphocytes will actually become activated. Within our ranks of B lymphocytes, and literally have millions of them, within those ranks of B lymphocytes, only a few are going to react to these antigens. So we're going to have an activation of a few B lymphocytes that are actually geared to these antigens, at which point they start to divide. So clonal expansion is a process of cell division. So you might write down cell division or write down mitosis next to clonal expansion. Now, the idea here is that these few activated B lymphocytes start to divide and divide and divide and divide some more. And obviously, they make thousands and thousands and thousands of copies of themselves. Part of clonal expansion is, what do these cells become? As these cells divide, they don't just become one type of cell, they actually fall into two different groups. Some cells produced out of clonal expansion we're going to refer to as plasma or effector B cells. Plasma cells or effector B cells are cells that produce antibodies. So you might draw an arrow from plasma effector B cells to antibody production. These cells stay in the lymphatic system. These cells crank out proteins. Specifically, they're proteins called immunoglobulins. We'll see that on the next slide. And those proteins, those immunoglobulins, are antibodies, and they will circulate through our bloodstream, and they will do the job in destroying the foreign agent. Then there's another group of cells that are actually produced in the process of clonal expansion, and these are called memory B cells. Memory B cells also remain in the lymphatic system, but their job, as the name implies, is to remember those antigens. So what they do is they give you a permanent memory, so that if this thing should ever show up again, it's almost like your immune system goes through the computer and finds exactly what those antigens are, and very, very quickly comes up with a body defense mechanism. And so you can respond to it almost immediately. So we're going to make antibodies. And these antibodies are going to be proteins that do the job of defending us. Now, the last bullet point here is that once these antibodies have destroyed this foreign agent, and once we're on the far side of that secondary immune response, I don't need those plasma cells anymore. So the plasma cells are going to specifically be killed off. It's a form of programmed cell death that's officially referred to as apoptosis. Please be sure you keep that term in mind. Apoptosis is programmed cell death, and it's just very simply a way that we can get rid of cells that we no longer need. Now, on the other hand, just keep in mind we still have the memory cells, and it really doesn't take long for a memory cell to become activated and start cranking out plasma cells that will then make the antibodies that we could use if we should ever encounter this foreign agent again. Well, here's an illustration that basically shows this idea of clonal expansion. You take a look at the picture here, you'll see the top row of cells. Those are all B lymphocytes. Of those B lymphocytes, only one, the one that's kind of in the middle, is going to become activated. Now, once it becomes activated, it starts to divide. And so I see the series of arrows indicates me the process of cell divisions leading to a bunch of plasma cells on the right and leading to a bunch of memory cells on the left. So the B lymphocytes stay in the lymphatic system, and it's the antibodies that do the dirty work. We had mentioned antibodies are proteins. They belong to a group of proteins referred to as the immunoglobulins. They are antigen specific. If you take a look at the illustration at right, you will see that an antibody is shaped like the letter Y. At the tops of the arms of the Y are antigen-specific binding sites. So that little itty-bitty Y-shaped molecule, which really isn't so itty-bitty, it's a big giant protein, will bind to the foreign agent. In doing so, it can affect direct neutralization of the foreign agent. In other words, take it out of circulation. It can enhance phagocytosis for those white blood cells that are on site. It can inspire cytotoxicity, which will kill the foreign agent, and it can furthermore activate, complement that set of proteins that can themselves burst the foreign agent through the form of membrane attack complexes. It can enhance phagocytosis and in turn stimulate the inflammatory response. So not only does this slide tell me about antibodies, but it really, really reinforces this idea of crosstalk between all these mechanisms, and all of these mechanisms are operating pretty much at the same time, being very, very effective in protecting me. Well, now let's take a look at cell-mediated immunity. In this case, there's these cells called T lymphocytes, or T cells. And the T lymphocytes, or the T cells, are going to fight the foreign invader directly. They will do so through the same mechanism we saw with the B lymphocytes, or the B cells, clonal selection theory. And we'll even see an illustration in a moment. Remember, clonal selection theory began with exposure, so not only are our macrophages displaying antigens to our B cells, they're also exposing them to our T cells. Among all of our T lymphocytes, only a few will become activated when exposed to those antigens. But those T cells, when they are activated, will go through this process called clonal expansion, cell division, mitosis. And as they divide, they're going to produce a number of different cells that will have specific jobs to do. The first cell type I see down here are what are referred to as cytotoxic T cells. Sometimes they're called effector T cells, and I have even heard them referred to as killer T cells. But these particular cells produce a number of different proteins, in particular one called perforin, that will actually specifically destroy the bacterium by more or less causing it to burst. Then amongst these clones that are being produced, there'll also be a group of cells called helper T cells, and their job is not specifically to combat the foreign agent, but their job is to create a line of communication between cell-mediated immunity and antibody-mediated immunity. Finally, we're going to make a group of cells called memory T cells that basically do exactly the same thing that memory B cells did. They're going to remain in the lymphatic system and be an encyclopedia of knowledge concerning these antigens, so that if anything like that shows up again, you quickly make that reference and come up with the T lymphocytes that will effectively combat and destroy this thing before it ever has a chance to make you sick. Now, the very last bullet point mentions something that we have identified before, and that is the word apoptosis. Remember, that's programmed cell death. The bottom line is, once an infective event is over, I will not need those cytotoxic T cells anymore. They will self-destruct. That's called apoptosis. I will not need those helper T cells anymore. They will self-destruct. That is apoptosis. I will keep the memory T cells, but the other ones that are actually involved in the active combat against this foreign agent, I don't need anymore, and so they will be removed. In a nutshell, this illustration shows me antigenic exposure. At the left, those antigens are being presented, and I go through a series of clonal expansion events leading me to the production of helper T cells, memory T cells, and cytotoxic T cells. I see them labeled and illustrated on the right. All right, I'm sure you're going to be glad to hear that this is the actual last slide in this presentation we're going to deal with. In terms of immunity, we're going to make a distinction between active immunity and passive immunity. And in each type, there is active natural, there's passive natural, there's active induced, and there's passive induced. There's going to be basic differences in how you get that immunity. There's going to be basic differences in terms of what that immunity does for you. First off, we'll start with active immunity. You're going to need to write stuff down. Next to active immunity, I want you to write down direct exposure to antigens. Direct exposure to antigens. Then you're going to write down memory cells made. Memory cells made. And then finally, you're going to write down immunity permanent. Immunity permanent. So let's see what's involved here. I mentioned that when I was 4 years old, I had chickenpox. That's a case of active natural immunity. Natural immunity is when you actually get the disease. I was exposed to it. I got it. I was 4 years old. And in that process, I was being exposed directly to those antigens. And my body defense mechanisms got into play and recognized that fact. I fought off the chickenpox. But in my immune system, I had these memory B cells and these memory T cells that to this day, over 50 years later, are still in my body that remember the fact that that chickenpox was on my doorstep once upon a time. And I will never, ever get chickenpox again. Now, there's another way of getting active immunity, and that's getting it through a vaccination. That's why we're going to use the bullet point induced here. So when you get a vaccine, sometimes, not all the time, but sometimes that vaccine will contain a killed or inactive version of that foreign agent. It cannot make you sick, but that vaccine will contain those same antigens. Inject you with the vaccine, you're exposed to the antigens, your body defense mechanisms do exactly what they would have done if you actually had a virulent form of the disease. So you get direct exposure, you get the memory cells, and you get permanent protection. Now, on the other hand, there is a second type of immunity called passive immunity. And next to passive immunity, we're going to write down three things, kind of like we did before. And the first thing I want you to write down is passive immunity involves indirect exposure to antigens. Indirect exposure to antigens. The second thing you'll write down is no memory cells made. No memory cells made. And the third thing you're going to write down is immunity is temporary. Immunity is temporary. So how does it work? I'm going to do the same thing I did before. In terms of passive immunity, probably the best example of natural passive immunity is when a woman has a baby. And in having that baby, she is going to nurse that baby. Now, in the process of nursing the baby, and as a matter of fact, in the process of that baby developing the womb, some of mom's antibodies are moving from the placenta into the bloodstream of the baby. So the baby is actually borrowing antibodies from mom. The fact of the matter is the baby is not being exposed to those antigens directly. So baby gets a bunch of antibodies, and either that's through the placenta in the process of gestation, or later on in the process of getting milk from mom, that baby still will receive some antibodies. But those antibodies only last a certain length of time. They're proteins. They have a limited lifespan, so baby's immunity only lasts as long as those proteins last. But what it does, it gives baby one step up, and so at some point baby will develop his or her own body defense mechanisms, but this form of passive immunity passed on from mom to child gives that baby a little bit of a head start. Now, there's another example here, which is going to involve vaccination once again. Now, in this case, the vaccine is generally going to contain antibodies. So, for example, in World War II, American GIs were given a vaccination against hepatitis. Now, that vaccination against hepatitis was only good for a certain amount of time, because what they were doing is they were infecting, I believe it was cows, with hepatitis, and then they were extracting blood plasma from the cows and using that blood plasma as a means of creating this vaccine that contained the antibodies produced by the cow. So the GI gets the antibodies, the GI gets protection, but the protection only lasts as long as the antibodies last. So in the case of passive immunity, I'm going to tell you passive immunity is sometimes also referred to as borrowed immunity. Baby borrows his or her immunity from mom. In the case of the GI, he is basically borrowing his immunity from the cow, so to speak. So in each case, you've got a certain number of characteristic features that, at least in the case of active immunity, gives you permanent protection, but in the case of passive immunity, gives you only temporary protection. Okay, the remaining 5 slides in this presentation you're going to disregard. So at this point, you could just essentially bail from the presentation. All I am going to do is I'm going to have an audio on each slide that says disregard, and for all intents and purposes, when we got to passive versus active immunity, that's where the content ends for this particular presentation. Disregard this slide. Disregard this slide. Disregard this slide. Disregard this slide.